Okay, so last time we left off looking at the basic idea of arrays. And so we had added this array to our data segment called ARR1. And we use dword for the size specifier. And then we have the values, right? In this case, these three values in the array, where these values were all being represented in terms of hexadecimal. And we also hit on the fact last week that we know that when we're dealing with a hexadecimal value that is going to have a letter between A through F as the MSH or the most significant hex symbol, that we have to have that leading 0 in the beginning. So the rule there was that because variables can also start with letters, we have to have a way to distinguish them from things like a hexadecimal value. And so the rule there was that, again, you had to have a leading 0 if your hex value was going to have a letter A through F as the MSH, right, or the most significant hex symbol. And so we said that you can always tell whether the 0 is part of the number or not by just looking at the number, right, the total number of hexadecimal symbols. So here in particular, in our array of D words, when we look at the first term there, which is that 0, A, B, C, D, E, F, 1, 2 in hex, what we're seeing is that we have a total of 9 hexadecimal symbols. And so that means that the 0 itself is not part of the number, right, or part of the data. So the number itself, or the first element in the array, ARR1 itself, is just the last 8, right, out of the 9 hexadecimal symbols. So it means that the first term is that A, B, C, D, E, F, 1, 2 hex, right? The 0 is only there because of that rule that says that we can't have a value A through F, right? It's the first thing in our hexadecimal number. So we have to have that extra, in this case, that extra hex symbol to account for that. But since we have a total of 9 there, right, the assembler is going to know that that 0 is not actually part of the number. Whereas, if you, as we mentioned last week, if you had a 0 in the beginning, but you only had, a total of 8 hexadecimal symbols, well, then the 0 would be included as part of the data. So that was our first term, right? That really A, B, C, D, E, F, 1, 2 hex. And then over here, this was the second term in the array. And that one is written out as exactly, right, 8 hexadecimal symbols. So there's no extra leading 0, for example. And that's because that one we just wanted to be 1, 2, 3, 4, 5, 6, 7, 8 hex. So since the MSH is not a letter A through F, but rather just the number 1, we don't have to have any sort of extra 0 for that. So we just have exactly 8 hexadecimal symbols there. Right, and then the last term here, once again, we have a 0 in the beginning because of the fact that we have this F here. But we can look again at the total number of hex symbols there. Because we have the 0, and then we have the FD, CE, BA 74. And in particular, not including the 0, right, we have 8 hexadecimal symbols, meaning that, once again, the 0 is just not part of the data, but is just there because of that rule that says that we can't have a letter A through F as the first or most significant, or the first hex symbol there, since variables also start with letters. So that was the array that we looked at last time. So we just have 3 terms here, or 3 D words. And we also talked about the issue of memory, right? Because you always want to think about things like, well, what's happening in memory with my data? In this case, what's happening in memory? What's happening in memory with the array that we've declared array 1? And so we showed how to look at things like the memory pane in the registers pane. And one thing that we did is we also set columns to 1, right, in the memory pane. That way we can look at memory in more of a vertical sense where we're seeing each address on a separate line and we're only seeing 1 byte value per line. So in that way, we're able to see each of the individual addresses in memory, right, for the different variables that we're ultimately storing in memory. But here, since we're working with an array of D words, we really want to think about the issue of how are the individual bytes going to be stored. And we started to hit on that last week. And we talked about what was called little endian order, which is where the bytes are stored in reverse order compared to the way that we write them out. And then that concept, right, applies to any sort of D word, really anything that's bigger than a byte, right? But we're focused on 3 levels here in this class, really the byte level, the word level, or the D word level. But when you're working with something that's bigger than a byte in size, such as a word, which is comprised of 2 bytes, or a D word, which is comprised of 4 bytes, when you're working at those higher levels, we have to also think about, well, how are the individual bytes within that stored? And they're stored, as we saw last week, in the reverse order compared to the order that we write them out. And we apply that to each individual word or D word. So in this case, we have this array that has 3 values, right, or 3 terms within it. But the idea is we have to apply the rules of little endian order individually to each term. So when we build this and then step into it, and again, we know that we can do that with F11, and then F11 again. This time we're really focused on the data segment for now, and we'll add some more code instructions in a bit. So now we've stepped into this, and again, if you ever need to set those things up like the memory pane and the registers, remember that's under debug windows, and then you have your, your registers, memory, and watch window, as we've shown before. But here we already have our memory tab up. We have columns set to 1 here. So that way we can see each individual byte, each individual address on a separate line. And now we can look directly at array 1 in the memory pane. And remember that you can always pull up a specific variable that you have, right? Whether it's an array or not an array, right? Array just means that you have multiple values, right? Essentially, that are associated with that same identifier. And one way of setting up an array, as we're seeing here, is just in terms of a comma separated list of values. And then a little bit, we'll talk about other ways of potentially setting up an initial array. But with any identifier or variable name in your data segment, you can always go directly to that area in memory by, in this address field here, right? So we're in the memory pane, and then you have that field that says address. If you type in an ampersand and then the name of the variable or identifier that you want to jump to, it's going to take you directly to that location in memory, meaning that first byte that you'll see here is going to be where that variable starts in memory, right? Or where its first value is if it's an array, starts in memory. So in this case, for right now, we're focused on our D word array ARR1. And so again, the syntax there is just an ampersand and then ARR1. So it's sort of like how you would think about doing this in C++, right? Because one usage of the ampersand in C++ is also the address operator, right? To get the address of a variable. And it's used in somewhat of a similar way here. So address of array 1 is what we're going to plug in. Hit enter, and then you'll notice when you hit enter, it shows you what that address is. So in this case, that address 004040000, which is the usual start of the data segment, right? We've seen that with some of our previous tests that we've looked at. And so now we're seeing what that array looks like in memory, down here in the memory pane.
And so in particular, we focused on how the individual bytes are being stored, right? We said that everything was going to be reverse order. So that's why here the first byte is 1, 2, and then EF, and then CD, and then AB, right? So those 4 bytes together all are for the first of the 3 terms in the array 1 D-word array. But because of little ending orders, right, we always store the, the low byte first for that term. So that's why we have the 1, 2, and then the EF, and then the CD, and then the AB. And like we mentioned last time, the bytes, are going to be reversed if you actually, for example, move that into something like a register. And then right after that, right, so in this case, the first term, the 4 bytes for the first term are being stored at the address that ends in 0, the address that ends in 1, the address that ends in 2, and the address that ends in 3. And then the next 4 slots or bytes in memory are all for the second term, which is that 1, 2, 3, 4, 5, 6, 7, 8 hex. Meaning those 4 slots in memory, where again, because of little ending order, we're going to have the 7, 8 first, and then the 5, 6, and then the 3, 4, and then the 1, 2. And then the next 4 bytes is for the 4th term in the array. So the 7, 4, BA, CEFD, where again, we also recognized here that the 0 for the first term and the 0 for the third term were not actually part of the data, which is why, we don't see them here when we look at the individual bytes in the memory pane. So we're seeing then all the, byte individual bytes for this array. So in this case, we know that each individual D word is 4 bytes, right, or 4 slots in memory. So in terms of memory, right, the entire array takes up then 12 bytes. From, in this case, the address that ends in 0 all the way up to the address that ends in B or 11, right? So those 12 slots in memory. And if you keep going, you can scroll up and down here in the memory pane. So if we scroll down, right, we're just going to see the rest of the things that we have here, because we did last week, define other variables. We had this ARR2, which was a byte, right, in size. And this one we declared in binary format. Remember, you used the little h for hex and the little b for binary. And for decimal's the default, but you can also use a little d for decimal, but that part is really optional. And so if we scroll down here, and continue looking at memory, we're going to just see the other things that we've declared in the data segment. So you want to keep in mind that really the whole data segment, we said before that they're global variables, right? We haven't really talked yet about how to have separate procedures and local variables and all that, but we'll eventually see that as well. But everything that you have in your data segment here itself is essentially one big array, right? One big array in the sense that it's all stored back to back in memory. Whereas when we talk about array 1, we think of this as in more of the sort of traditional sense of an array, if you want to call it that, meaning like how we would think about an array in C++, right? Meaning we have values that are related and all stored together, right? Because we think of it as all 3 of these values are tied to or associated directly with the identifier array 1, right? Because we think of it as all 3 of these values are part of array 1, which on a conceptual level is how we typically think about this. But physically, what we're also seeing here is that really everything in the entire data segment is essentially one big array, right? It's all stored back to back. So that's why, the last byte that's stored for array 1 is the FD, right? Which is here. And then if you notice what's in the very next byte, at the address C there, it says F0, but that corresponds to exactly what we said here for array 2, right? because this was given as a binary value, but it's a binary value that has 4 ones, which corresponds to F in hex, right? And then 4 zeros, which corresponds to 0 in hex. So that's where we're getting the F0. And then we have some D words that we declared after that, and we see those here as well. So for example, the next 4 bytes you'll notice is 06000000. And so here we're also seeing what happens with little endian order if you decide to declare your data with decimal. So, we can work with all 3 numbering systems, right, in terms of our data, meaning for the values that we provide for variables, or literal values, right, for example, meaning literal values that we might use in the code segment. We can certainly provide the data in any 3 formats, right, meaning hexadecimal, decimal, or binary. But we also have to keep in mind that in the end, it's really all the same, right? Because in the end, everything is, physically ones and zeros. Everything is binary. So the idea is that we talk about little endian order, and meaning that you need to think about that when you're working with data that is larger than a byte in size, right? Such as a word or a D word. And we said that the individual bytes that make up the D word or the word, if you're working at that level, are stored in reverse order. And that applies regardless of which of binary, hex, or decimal you use in terms of listing out your data values. So what we're seeing here is we continue and work our way down the data segment. Now, we're down at val 1, and then val 2 and val 3. And the next thing we see here is we see the 06 followed by 3 locations in memory that are all 00. But we also want to think about, well, why are we seeing that, right? Why are we seeing 06 and then 000000? Well, because that's exactly what we said, right? We said that val 1 was the value 6 in decimal as a D word, right? Meaning the value 6 as a 32-bit value. And if it's a 32-bit value, then that in terms of hexadecimal, that would be a hex number, right, with 8 hex symbols. And because that's how we typically display things in memory, right? And also registers, is we typically look at things in terms of hexadecimal, which is, of course, why we focused on that so much in chapter 1. And so you're seeing here that even though, we wrote it out in decimal instead of hex, this little endian order applies in the exact same way. So the idea is, 6 is a small value, right? We certainly don't need 32 bits to represent the value 6, but nonetheless, since the size here is D word, it is going to take up 32 bits. And that's going to be reflected in memory. So the idea is that when you look at these 4 bytes together, meaning these 4 consecutive slots in memory, right? Address D, address E, address F, and then the one that ends in 10 or 16, those 4 together are all storing the value 6. So the idea is that if you think about sign extension, and if you think about this in terms of hexadecimal, right, since that's how we display things here in memory, if you think about, well, what would the value 6 look like if it were given in hexadecimal with a total of 8 hex symbols? Well, it would be 7 zeros, right? And then the 6 at the end. So that's what your 8, that's what your 8 hex symbols would look like. And then from there, we're just applying the usual rules of little endian order. So that's the important thing that we have to keep in mind, right? So that declaration of val 1 is the same as this. If we had done something like this, same exact thing, right? It's just we're using two different numbering systems here. So that's how we're getting what we got here on those 4 lines. So because when we apply the rules in linear order, we're going to store that byte first, and then this byte, right? And then this byte, and then that byte. So that's how we're getting that. So all 4 of these are for the value 6. And then likewise, it's the similar idea for the 7 and the 8, right? So continuing here, we have the 4 bytes for the 7, the 0, 7 followed by the 3 sets of 0, 0, or the 3 bytes of 0, 0, and then the 0, 8, right, followed by the 3 bytes of 0, 0. And then again, for the remaining things, because we're certainly not using all the memory, right, for the data segment. So that's why we're seeing a bunch of zeros after that. And then, as we mentioned last week, also the question mark, remember, really corresponds to 0 as well. But it symbolizes uninitialized data.